Hello, my name is Andy Minoski. I'm one of the members of the Vault team. Specifically, I'm the product manager for what we call platform security, as well as all the cryptography features in Vault. And what I'd like to talk to you about today is post-quantum cryptography. It's a pretty cool sounding Star Trek term, but in reality, these are kind of futuristic topics that we have to think about today when we talk about how do we build a product like Vault that's supposed to defend and protect sensitive information for 10 plus years. Really quick background on who I am. I've been with HashiCorp for about 4 years now. I joined pretty early on to lead the development of what became Vault Enterprise, as well as the evolution of Vault from around Vault 0.5/0.6 until today at Vault 1.3. Now we have a much larger Vault team, as well as I have other colleagues in the product management team. And today I focus specifically on cryptography, as well as how Vault protects all of its data at rest and in flight. I spent most of my career in cryptography. I used to formerly run product management for encryption and product security at NetApp, as well as focusing on defense and systems that are sort of more US federal related with regards to how cryptography and encryption protects sensitive information both in flight and at rest. And I spent my time in college focusing on this as well, with degrees focused on specifically cryptography on the CS side, and then game theory and quantitative economics, which is some of the math that goes into actually some of the things we're going to talk about with regards to quantum cryptography. Really quickly also, this is, there's a lot of things that this talk is and isn't. More importantly, this talk is not a very exhaustive review on quantum computing and sort of all of the nuances and physics therein. There are some fantastic talks out there that I would heavily recommend that you take a look at. Most notably, Steinkirk's talk at DEF CON 23 on hacking quantum cryptography is a fantastic talk that goes into really the nitty-gritty details of quantum computing, as well as some of the algorithms that we're going to talk about today that we have to think about when we build Vault. This is really more of a practitioner level review of sort of what are some of the nouns and verbs around quantum computing, and then ultimately kind of a review on how a product like Vault tries to think about things like this when we build cryptographic systems, key management systems, kind of sensitive internals within Vault. So why do we care about quantum cryptography? Well, quantum cryptography is a very cool topic, and quantum computing as a whole is a very cool sounding topic. But the real reason why we care is something called perfect forward secrecy, or PFS. And PFS is an information security principle that really says, computing power is going to advance. There's going to be sort of an advancement of technology as well as resources from different types of adversaries. If we want to protect sensitive information, we need to make sure that that sensitive information is protected, both here as well as, going forward with like significant advances in technology. So, when we built Vault knowing with the idea that PFS is something that we want to, really maintain. And if we're going to maintain PFS, we do need to look onto the horizon of kind of like future threats, especially when these are threats that could, reasonably happen within the next decade or so. So to really kind of review what those potential threats and opportunities are with regards to quantum computing and quantum cryptography, we probably need to talk a little bit about quantum mechanics and how some of the magic happens associated with potential code breaking. So quantum mechanics is hard for a number of reasons, but one of the biggest challenges associated with quantum mechanics is that we don't really know where anything is ever. And that's because of two key principles, something called the Heisenberg uncertainty principle, which most folks might recognize from physics or sci-fi, where there's a box and there's a kitten in it. If I open the box, things happen, et cetera, as well as the observer effect. And what these both kind of tantamount down to is that there's a lack of precision that happens when I try to focus in on the position of a particle, as well as the momentum of that particle or the velocity of that particle. I can't focus on both simultaneously and get exact precision. So instead of trying to figure out exactly where things are, and also if I measure it, I impact that system. So the combination of those two things together mean that if we really want to know where something is from a quantum computing perspective, or rather from a quantum mechanics perspective as a whole, we have to estimate the answer. So we continually run a bunch of experiments, and then we build what we call a probability amplitude function, or a wave function. We can use that probability amplitude function to then be able to define something called a PDF, or a probability distribution function. If you took a class in like statistics or probability theory, either in like high school or college, you might recognize this. These are sort of like, if you've heard of like the t distribution or a normal distribution for like a grading curve. These are PDF functions, and what they really describe is they describe all of the states possible within a certain system, as well as the probabilities associated with actually seeing those states. Quantum computing, or rather quantum mechanics, kind of introduces a number of topics then that kind of get challenging to grasp And so I think one of the ways that I've found, at least, to be able to grok some of this stuff a little bit better, and many other members of the Vault team have, is to really think about this less in sort of the how does this actually work from a physics point of view, and think about it really as math. So when we looked at that, like that curve, that probability distribution function, that's representative of a quantum system. And just like other types of like waveforms, I can do a lot of things to that that are representative in the real world, in this case, of quantum mechanical interactions. The first is what we call superposition. And this is really the idea that you can have two waves that mash together to create a displacement wave. And then, as a result of all that, you have a system where everything there is A, holding multiple values simultaneously, and then B, further entangled. And the best way to think about this, other than thinking about kind of this interaction here of multiple waves creating a displacement wave, is to think about how water works. So if you've ever kind of gone over to the ocean shore and watched two waves crash together, there's a resulting displacement wave that is created, sort of the kind of black wave that we see here. But there's also an impact that happens on the two waves that hit each other initially. They are perturbed by sort of that interaction, and that's the process of entanglement. This combination of holding multiple state values simultaneously, which is a function of the fact that, again, we're not really looking at one single individual instance. We're looking at this like distribution function that represents all possible values, as well as the fact that the interaction there yields a sort of relationship between the two initial systems. Allows us to be able to, via these principles of superposition and entanglement, simulate some pretty exciting sort of interactions from a computing perspective. And let's go talk about that. So when we think about regular computers, there is this concept called a bit. And the idea here is that, I can, set a charge that's associated with either an electron passing into a certain kind of place, or there being no electron there. Basically, like I have a switch where like I've turned the light switch on because it's charged, or there's nothing there and the light switch is off. I can set up gates and other kinds of arrangements of those switches to effectively program an interaction that could be a numerical interaction like 1 + 1 = 2, or a more complex interaction like a compiled program. And the net result of that is what we have today with digital computers. Quantum computers, however, are a little bit different. Because of the properties of superposition and entanglement, I have a lot more states that are possible, because I'm not really, again, looking at whether or not the light switch has been flipped on or flipped off. The challenges of quantum mechanics, specifically around measurement, yield me actually a pretty exciting opportunity, which is instead I'm looking at the possible spin of the subatomic particle, which the consequences of that being that I have a lot of different states. And we see this here. If you kind of ever go look in quantum computing or quantum mechanics kind of like literature, you'll see this design here, the bottom right-hand side. That's what we call a block sphere. And the block sphere is representative of all the possible states associated with a qubit. So this is a lot more states than the 0 or 1 that we see in binary. This is actually well, you can actually derive the number of states from it, but basically there's a significant amount more that I can effectively cram into a qubit than I could otherwise cram into an irregular bit. Now, the benefit of this is that just like digital computers, quantum computers are programmable. So if you're familiar with computer science, there's a lot of stuff that you've heard about like Turing machines and sort of like what I can and cannot do with these systems. Quantum computers are very powerful systems that, just like another regular computer, I can simulate a lot of operations on. They're also very, very parallelizable. So like, just like we were talking about before, some of these concepts of whether or not I can, split up a computing transaction on a classical or digital computer, there's a lot of things that I got to think about associated with how I sort of divide up time. Well, I don't need to divide up time or resources on the quantum computer in this regard, because again, I'm measuring the whole probability distribution function that I'm deriving from all the waveforms that are happening that I measure from the system of interactions. This is really cool because I can suddenly parallelize things to a potentially infinite amount. But there is no such thing as a free lunch. First of all, quantum computers compared to classical computers, and this is something that we don't talk about a lot outside of kind of like academia, they're kind of slow. And they're not slow because they're inherently slower as a function of like the interactions going on. They're slower because I have to run kind of a number of simulations that happen over and over and over again, and then error correct back to that waveform that I can then use to derive a PDF. So, when I want to do 1 + 1 = 2, what I'm doing with a digital computer is I'm effectively saying I'm going to set up an arrangement of gates. I then shoot electricity down them, and if it lands on a certain set of arrays, I mark that down in binary representing 1 + 1 = 2. Kind of goes off in one hitch. Quantum computer, what I'm doing instead is I'm setting up a series of interactions. I run it, it blows up, I measure it, and then I do that like 1 billion times, and then I use a bunch of probability theory to sort of assert what I believe probabilistically is the result of that based off the PDF that I've gotten. It's a lot more complicated. And unfortunately, the complexity associated with that is passed on to the developer in some aspects. Today, there are libraries associated with kind of like commercial quantum computers, like IBM has a series of like commercial quantum computers that are available. There's a lot of contention around whether or not they're actually full quantum computers for some of these commercial ones, but I will leave that to you to determine. The reality here, though, is that this isn't like just like writing code normally. There is a lot that you have to kind of think about when implementing algorithms here. And today we're still at the infancy of quantum computing, so we're still also the infancy of ensuring that the developer experience there is really solid. Today, like I said, this is the beginning of quantum computing. QCs, or quantum computers today, are slow, ungainly, and expensive. Most powerful quantum computers are still under 100 qubits, and they're able to run and implement some kinds of algorithms. In fact, some that we're going to even talk about today, but they're still very challenging. The economics of running a quantum computer are very much weighted against any kind of commercial operations with them, and they're typically only used for certain types of like scientific or cryptologic processes, and even then at a very basic level. But technology here is improving very rapidly. So one of the things that we've noticed with quantum computers over the 2010s is that they seem to be improving at a doubly exponential rate, which has led to the kind of conception of something that's been called Nevin's law. And this is like the quantum computing version of Moore's law. So instead of having transistors double once every 18 months, Nevin's law says that, QC, like basically computing capabilities, are improving at this doubly exponentially rate, which is much, much faster. So there's a serious question right now about whether or not quantum computers are going to be economically feasible in the relatively near term, like in the 2030s or possibly at latest like 2040s or 2050s. This is very possible, and as a result, we need to start asking some serious questions about cryptography. So what are those questions? Well, when I want to break cryptography, there's really 2 ways for me to break crypto. The first is I go around the math, which is kind of the 99.9% of the time example. If you really want to go break encryption to steal like a secret, I usually will try not to even touch the math, and instead, steal that secret from unencrypted places in memory. I will try to steal that secret by exploiting program code to be able to spy on a process that's going on. A really good example of this is the cold boot attacks that occurred on RSA. And so this is where the adversary was able to, and there are researchers here, was able to freeze the memory of a computer that was kind of comprising a key with liquid nitrogen and be able to extract that by monitoring the memory there. And extracting initialization vectors and other things that made the process for either guessing the key or establishing the RSA keys that were private easier. But if you do want to go into that kind of 1% example of going through the math as opposed to avoiding it, this is a process that we call cryptanalysis or cryptanalytics. The most easy example, or I guess kind of the most well-known example of cryptanalysis, is the GCHQ cryptanalysis on Enigma that happened in World War II. So in this case, Alan Turing and his team of cryptographers, using information that was exfiltrated to them from Polish intelligence before they fell to the Third Reich, was able to construct these computers that, given some information they knew about the Enigma crypto system, could help them better guess the potential initialization settings for whatever the Wehrmacht and sort of the Axis powers were using at that time, specifically for communicating like radio transmissions. So here, rather than kind of going around the math like a side channel attack, what we're really doing is we're exploiting knowledge of the system to better help us guess the original answer. And this is something that we do care about a lot in the context of quantum cryptography. When we think about quantum code breaking or quantum cryptanalytics, there are 2 cryptoanalytical algorithms, or rather 2 quantum computing algorithms that can be implemented for cryptoanalytics. The first is Shor's algorithm, which is really about reducing the complexity of factoring prime numbers. So if you're familiar with, or factoring for primes in a number. So if you're familiar with kind of going back to high school algebra, finding like lowest common factors or greatest common factors, how do I find like certain types of prime factors that exist for numbers? Shor's is very, very good at that. There's another one that we talk about less, which is called Grover's algorithm, which is kind of the difficulty of searching for an individual specific piece of detail. To understand really why cryptographers are concerned about quantum computers, we need to dive a little bit deeper into how both of these algorithms work. Shor's algorithm is the one that kind of everyone is most concerned about when it comes to quantum cryptanalytics. What Shor's does is it really allows quantum computers the ability to be able to search for factors for any kind of large number much faster than a traditional method. So the traditional method that we use to search for factors and then look for certain types of prime factors for that is something that we call number sieve right now. And number sieves are basically ways to build on kind of checking to see whether or not a number is divisible by another number, and then using properties of like things that we call memoization, which is sort of memorizing specific kind of like sub answers to certain types of problems, or using things like dynamic programming, which is the process of dividing and conquering an algorithm up into kind of like optimal sub problems that you can reassemble. So on a traditional computer, we can do these things and be able to sieve out the numbers that are associated with the factors for a number. With a quantum computer instead, what I can do with Shor is turn this into a separate kind of problem, something we call a period finding problem. So looking for sort of like a rate of the existence of a certain prime number. That process using something that we call a quantum fast Fourier transform, which is basically like a heavily parallelized via the mechanics of quantum computing fast Fourier transform, we can speed up the process for searching for these prime numbers that are factors for another number to a much faster degree by, like orders of magnitude. The result of this is that if you're running, if you've implemented in Shor's on a powerful enough quantum computer and you run it, you can drop the time associated with breaking certain types of cryptography that are based off of the factoring of prime numbers, the difficulty of factoring prime numbers to significantly. Something that would take, decades or longer than the heat death of the universe could take, a year or minutes, depending upon the cryptography associated with it. We rely on the difficulty of factoring these numbers for a number of different aspects of computing and cryptography. Most notably, we rely on them for kind of the secure communication cryptography that we use for aspects of the internet like SSL and TLS. So a lot of public key infrastructure that serves as the backbone of that, that information is reliant upon the difficulty of factoring these large numbers and searching for primes. The algorithms like RSA, which are used for kind of public key cryptography, for verifying the integrity of a digital signature or an identity, these are immediately vulnerable to a quantum computer with Shor's. Another set of algorithms that are focused on how I transfer secure key material for the use of further cryptography, what we call key exchange algorithms, are also vulnerable to Shor's. There's a very, very popular algorithm we call Diffie-Hellman that focuses on the protection of a sensitive piece of information where you establish kind of a usually ephemeral channel that exists between two parties and then send over data that could then be used to comprise later cryptographic sessions. Diffie-Hellman relies on the difficulty of something called the discrete log problem, which basically means that, if you've taken high school algebra, you've probably seen logarithms before. There's a certain type of logarithm that exists where there's been an operation that happens that you need to kind of untease as part of that logarithm. Taking a discrete logarithm in that regard is very, very computationally difficult, but there's a way of using Shor's algorithm to be able to basically solve that discrete log problem with the same kind of effectiveness that you would for that other factoring problem because of how Shor's works. So this means that I can have a much more computationally efficient discrete log algorithms. And as a result of that, we have a serious problem because Diffie-Hellman is now vulnerable to a attack. ECDSA, which is used for elliptic curve cryptography's digital signature algorithm suite, is also vulnerable because it relies on similar mathematic protections. And the consequence is that on a powerful enough quantum computer, many of the algorithms that we use for identification in SSL and TLS, PKI infrastructure, and even things like Bitcoin are vulnerable to attack from Shor's powered cryptanalytics. Shor's isn't the only thing in quantum cryptography. The other big area of concern is something called Grover's algorithm. Grover's algorithm is an algorithm that focuses on speeding up the process for searching for something. We call searching for a black box, an input to a black box function. And the way to think about Grover's is it's kind of like a ultra parallelized database search algorithm. If I want to figure out where the index is of a specific value, I could, immediately go through that database and look through every single possible value in the database, find the value and say, hey, here's the index of it. Grover's is sort of like, what if I could infinitely parallelize that with a quantum computer and then kind of tease out the answer? The result of that is that I can have a quadratic speed up of the algorithm time, which means it's a lot faster to be able to run Grover's to search for inputs to this kind of black boxed function or search for the index of this certain like element in a database. That's still a lot slower than the Shor's speed up that we see on searching for factors, but suffice to say it's significant. The consequence of Grover's algorithm is that a lot of weaker ciphers that we've been concerned about for a while, just because computers are going to get faster over the course of the next few decades, get a lot weaker. Things like AS128, Blowfish for symmetric key ciphers, as well as weaker hash algorithms are kind of, a lot more subject to issues related to possible quantum computing, because I don't need to necessarily wait for kind of better parallelizable processors or other kind of highly parallelizable programming languages or frameworks come out. I could potentially run this on a powerful enough quantum computer. That being said, a lot of these kind of what we would consider weaker algorithms or key lengths, these are things that are already on the way out. So, a good example of this is that AES-128 has been largely invalidated in form versus AES-256 variants for kind of minimum levels of protection for protecting top secret information in the US government, for example. So is quantum computing a threat? Honestly, not really today. This is stuff that requires a level of computing that is orders of magnitude more powerful than the quantum computer that we have. That's kind of like Google's quantum computer. Or any other kind of publicly known quantum computer. Sycamore and some of the other kind of large research quantum computers are still 3 orders of magnitude too small to be able to run Shors on kind of powerful enough data. But like we talked about before, things are advancing relatively quickly. Nevin's law means that quantum computing is advancing at a very, very fast rate. So there is some pretty serious concern that within the next decade, we could actually start to see quantum computers that are able to implement some of these algorithms to run crypto analytics on classical cryptography. And if there are advances in the areas of error correction, especially, we're going to get there a lot faster over the course of the next decade. It's kind of anyone's guess to see whether or not that's going to happen. But if you're a cryptographer and you're thinking about this from a security perspective, that's good enough for you to stop and say, hey, we really need to be concerned about this and start to take some collective action. And the collective action that we've taken, at least in the Western world, is something called the PQCSP, or the Post-Quantum Cryptographic Standardization Project. This is a project that's been running for the last few years, run by the US and Canadian governments. And what PQCSP is evaluating sort of the impact of things like Shors and Grovers on traditional cryptography, and what do we need to establish from a standards perspective to ensure that we can protect data going forward, even in the face of quantum computing. The result of the PQCSP is that there are a number of changes coming to some documents that most of the Western security world look to for sort of the exemplars of good cryptography. The most important document there is something called FIPS 140, or the Federal Information Processing Standard 140. This is a summary of all of these kind of other NIST guidelines, the SB 800 suite, that really stipulate what the US and Canadian governments feel is representative of good cryptography for different types of good use cases. So that means that we need to start rethinking about whether or not we want to implement certain types of new algorithms or whether other previous algorithms were safe, given that there is an upcoming change to what we would consider the threat model for good, state-sponsored adversaries and other kind of advanced adversaries, given that they might be powered with quantum computers in the next decade. All right, so the world right now is thinking about quantum computing. You'll hear about this a lot, kind of from security vendors as well as from academia. This is a real topic for us in Vault, and this is something that we've been thinking about in Vault since the kind of inception of Vault in 2015 and the inception of Vault Enterprise in 2016. We respect the fact that we really want to build, in collaboration with the open source community, a product that has a lasting product. One of the things that if you ever talk to us here at HashiCorp directly about our vision, we share the idea that we are building products and working with the community to build projects that are built for a dynamic world, a world of dynamic infrastructure, where you are going to change aspects of your infrastructure, but the workflows associated with what's going to run on that infrastructure won't change. And the same thing is the case with Vault. The challenge associated with quantum cryptanalytics is one that we're very concerned about, but it's one that we have to get over if we're going to really build something that is sort of the last secrets management process, like tool that you need to use or implement within your infrastructure. So the implications of this are that if in a post-quantum world, we really need to do two things. The first is we need to defend against quantum cryptanalysis, data in flight, at rest, as well as like aligning with compliance requirements in the future. The second one is to utilize post-quantum cryptography. You know, quantum computers give us some cool benefits. It's not all just bad. And so we would like to leverage those in proofing the cryptography and security within Vault. In terms of post-quantum cryptanalytics, defending against those Shors and Grovers things we talked about, well, in Vault, there's something very important called the cryptographic barrier. And this is the data that sits at rest and the sheathing of cryptography that exists to protect the data. Vault doesn't inherently trust its storage backend. It requires that it's available, but it doesn't trust it to protect the data. So it handles all of its own key management and encryption of the data there using a cipher. In this case, we use the AES-256 GCM cipher, which is one that we've actually specifically chosen because it's resistant to Grovers. We also actively try not to use known kind of quantum vulnerable algorithms, either in key exchange mechanisms or anything else that is kind of operating on defending Vault's critical security parameters. And that's twofold. One, to ensure that we're not kind of broadening the possible window of threats related to Shor's algorithm. The other one is that critical security parameters are what FIPS 140 cares about. When you think about sort of building a cryptographic module, something that encrypts data and manages keys, what you really, really care about for a lot of these kind of like regulations like FIPS is these critical security parameters that manage how those keys are protected, like handled, et cetera. And so if we can at least remove as much as possible these vulnerable pieces of cryptography there, we're in a good spot. But like I said, it's not all bad. And quantum computers are awesome. They provide us a lot of other cool, unique benefits in the future, not just from a scientific computing perspective or a code breaking perspective, but also from the ability for us to be able to better proof our systems against security. So today, that PQCSP process is sort of igniting like a firestorm of research that's been going on for the last 5 years in computing and advanced mathematics. And one area that's very exciting there is that there's been a lot of new ciphers that have been coming out and proven to be particularly viable, not just defending against quantum computing attacks, but also security in general. So one, Cha-Cha 20 Poly 1305, which is kind of being billed as the possible successor to AES. That's already in Vault. We introduced it into Vault in 2018 once it came into the Golang core. And that's something that this is kind of highlighting the process that PQCSP is producing a lot of kind of new alternatives to cryptography that have benefits not just in sort of protecting against quantum cryptoanalytics, but also in making it faster and easier to protect data. And today, actually, there are quantum computers that exist, and they are actually some commercial quantum computers exist. And the reason why they're viable, and it's not like even in the face of it being difficult to do cryptoanalytical attacks, is the fact they generate a lot of entropy or random numbers. Anytime you measure a quantum system, it blows up on you, and that blow up process is fully random. We can leverage that blow up today in Vault. If you're using any of these kind of like next generation HSMs to be able to inject more entropy into Vault, which is used to, again, protect those critical security parameters, but also to feed new systems like transit and other kinds of things that we're working on for random number generation for keys. So I've only got a few more minutes left and I want to open it up for questions, but the short answer here is that quantum computing is serious. This is a topic that we take very seriously from like a security and cryptography point of view, but it's really not a threat right now. This isn't something that's going to kind of jump up and bite you tomorrow or even in the next few years. It, however, is a concern if you want to start protecting data past this decade. If Nevin's law shakes out the way that it does, there is the possibility that you can start running some of these cryptoanalytical algorithms, possibly in the late 2030s and then even in the early 2040s. And if there are improvements in error correction technology or material science that we didn't think about that come into play, that's probably going to be a lot faster. The implication of that is that governance and regulatory requirements around cryptography are going to change. In fact, they're changing right now to factor for sort of these like new types of threats from quantum computers. And so with Vault, at least, it's a concern for us just because we want to make sure that you can write sort of your own ACL policies or Sentinel policies, et cetera, in one way and protect a workflow, not just today, but into the next decade and beyond. If we want to do that, we have to start thinking about quantum computing. And that is quantum computing and quantum cryptography.
Wow. I have to say that was an amazing talk, Andy. So we actually have quite some time for questions. And I have two from the chat, and I'm not going to pretend that I understand anything what they're saying, but I'm sure you will. So the status of FIPS 142, that makes sense to you? Good.
Yes.
For Vault was issued around 0.9 things. What is the current status? Does it, well, let's first just answer that one. What is the current status of that?
Yeah, so when we look at FIPS 140 and Vault, one of the primary concerns that we have is about, if you're in either like a FedRAMP medium or high environment or somewhere else where you need to attest FIPS 140 compliance, you need to use a FIPS 140 certified crypto module. Golang, which is the language that we use to program Vault, as well as most of the other products here at HashiCorp, does not have a natively certified FIPS 140-2 module. So instead, what we did is we worked with our auditors, as well as folks in the academic research community and the federal government, to be able to provide a process that allows us to be able to sheathe all of Vault's data with external cryptography. So the letter that you'll see on our website, which is from Leidos, is attesting to the fact that that process is able to sheathe our sort of the cryptographic security parameters, or the critical security parameters, the CSPs that we're talking about in here, with encryption from that external device, typically an HSM. And the result of that is that Vault, from a FIPS perspective, says, look, if you don't like our crypto module, go sheathe it in cryptography from your HSM and use that as sort of your FIPS 140 device. Kind of like throw a blanket over the problem. So that hasn't changed in Vault. CLWRAP today is still used, and we have many customers that are subject to FIPS 140 pursuant to like FedRAMP, as well as kind of like other federal use cases where that's necessary. And so that doesn't change also because, again, we don't have like a special crypto module involved for it. We just have this process that reaches out to another external system and then sheathes everything in external cryptography. It's important, though, is that FIPS 140-2 isn't the current version of FIPS anymore. 140 has a new version, FIPS 140-3. And 140-3 actually factors for things like Vault to be able to certify themselves at what we call a hybrid crypto module. So it could be a hybrid software module where Vault is working in concert with something like an HSM to be able to import in the necessary components for random number generation, as well as like different aspects of cryptography to basically certify the existing architecture that we have with CLWRAP. And do it so natively. So we are investigating that right now for Vault Enterprise, and we'll have more information about that hopefully sometime later in 2020. But right now, CLWRAP was and is, remains this process. And if you have any questions on that, highly encourage you to take a look at the audit results that exist on the compliance page for Vault.
Okay. And the way we've implemented, does that mean that it'll automatically apply for every new version as well?
Yes. So if you, for example, are using CLWRAP and you upgrade Vault, it's a transparent process from an upgrade perspective. So going from like Vault to, let's say, like, if you're in like Vault 1.3 today and you go to Vault 1.4, 1.5, or 1.6, et cetera, the CLWRAP process isn't going to change any of your upgrade parameters. It's just, again, it's reaching out to the external crypto module and allowing it to do its magic and saying, hey, when you have an auditor question, you'll point to that. If we do achieve a native certification for the CLWRAP architecture with FIPS 140-3, there will be no implication or code changes on Vault, which is really cool. What we're just basically saying is that we'll now have a certified like NIST page that says you have a FIPS 140-3 certified crypto module. And it's okay with us because now we have a way to test for like your hybrid style of using an HSM or some other external system to leverage for random number generation and other things.
Okay, very cool. I also have a question from chat that asks if you have any recommendations for good books on quantum computing.
Ooh,
that's or quantum cryptography. I don't know. QC could be anything.
Yeah, so I think if we're talking about quantum computing with QC, honestly, there's a bunch. I would actually recommend before jumping into that. So I gave a recommendation to a DEF CON 23 talk on like quantum computing that goes into the physics of that. There's a set of recommendations that physicist that gave that talk actually has there. I would highly look at that. But in all honesty, if you're talking about quantum cryptography, this is really just cryptography at the end of the day. Like the quantum computer, like the mechanics of quantum mechanics allow quantum computers to do some really cool things around parallelization and sort of basically ways to allow an adversary to potentially guess certain types of keys faster. But the math doesn't change. And so this is going to be kind of a cop-out, but I would highly recommend from a book perspective, the CLRS, which is kind of, if you've taken computer science, it's that, Savess, Livingston, the R and RSA and Shamir, all of them, the kind of God book of algorithms. The math in there that kind of talks about factoring prime numbers, like how different types of algorithm speed up methods exist, not just from like period finding, which is what powers Shor's, but also things like, dynamic programming and memoization. A lot of that is contained in there. And if you kind of refresh yourself on that, I think you'll find that a lot of these kind of cool sci-fi topics, they're not as sci-fi as they sound. It's just, I have a different type of computer to run some of this math on.
Okay. And another question from Slack. Is there any 101 or cryptography for dummies for Nick and I to read?
So there's a bunch of different really good paths forward for it. If I was to say a book that's a good cryptography 101, Stamp's Introduction to Information Security is a fantastic book that kind of goes into an easy introduction to cryptography, as like sort of like, how do I frame things and like, what am I trying to do with cryptography at the end of the day? Like first, how do I use crypto? Why does it matter in the real world? And then slowly easing you into topics of cryptography, as well as kind of more complicated topics of information security. So the CLRS actually does cover some of the crypto here too. I mean, at the end of the day, crypto is really about how do I make it really hard for you to guess a number? And some of these, like the way that we implement that is kind of the reverse of thinking about how do I do something really efficiently. And so like what we call computational intractability, or sort of the difficulty associated with that, that's just basically all computer science. And so I would, between those two books, you're probably in a good place.
Okay,